When you think about probability, you probably think about like dice and coins. But let's just forget all that for a second. The truth is, probability is the hidden engine running our entire world. I mean, it's in your phone, it's keeping the power grid on. It's this secret language that industries use every single day to tame randomness. And today, we're going to open up that toolbox. So this is the big question, right? The one that keeps CEOs and engineers up at night. How do you possibly predict the unpredictable? I mean, think about it. A machine suddenly fails, a customer just walks away, a whole network crashes. These aren't just, abstract ideas. They're incredibly expensive realities. All right, so before we get to the solutions, let's first really understand the stakes here. I mean, what actually happens when randomness is just allowed to run wild in our industries? Okay, just picture this for a second. A single defective part could force a company to scrap an entire batch of products. One machine failure, that can halt a whole factory, just bring it to its knees. And a volatile market can literally erase millions of dollars in an afternoon. That is the real-world cost of uncertainty. So the thing is, we can't just get rid of randomness entirely. It's always going to be there. But we can manage it. And to do that, you don't need some magic crystal ball. What you need is a really powerful mathematical toolkit. Okay, so what's actually in this toolkit? Let's dive in and start with the absolute basics. So at its very core, probability is just about putting a number on uncertainty. That's it. So you ask a simple question, right? What's the actual chance that a part pulled off this assembly line is defective? And by calculating that one simple number, a factory can start making really smart decisions about quality control, about their testing, and even how many extra parts they need to have on hand. And here's where it starts to get really clever. Think about something like a backup system. Okay, on the one hand, you've got the addition rule. That helps us figure out the odds of at least one part failing. But then you've got the multiplication rule. And that calculates the much, much smaller and way more critical chance of both the main system and its backup failing at the same time. This is the fundamental math that allows us to build incredibly reliable systems. Okay, but this is where things get really powerful. I mean, the basic tools are great for taking a snapshot in time, but we all know the world is constantly changing, right? The real magic, the game changer, is when we can start getting smarter and actually update our predictions as new information rolls in. This whole idea is called conditional probability. And that little phrase, given that, that's everything. It's the key. We're not just asking, hey, what's the chance this machine will fail anymore? Now we're asking a much smarter question. What's the chance this machine will fail, given that we're seeing it vibrate more than usual? And boom, there's the payoff. This isn't just theory, math on a whiteboard. This is the absolute heart of predictive maintenance. An engineer sees that probability suddenly spike, and they know, okay, it's time to act. And that lets them prevent a super costly breakdown before it even happens. Now, the engine that drives this incredible kind of updating is something called Bayes' theorem. And look, instead of thinking of it as some scary, complex formula, I absolutely love this description. Just think of it as a belief updating machine. It's actually a beautifully logical process. Look, you start with an initial belief, right? Like, this sensor is probably working just fine. Then you get some new evidence. Let's say the sensor gives a really weird, out-of-the-ordinary reading. Well, the theorem lets you precisely calculate how that new evidence should change your original belief. And this logic, it powers everything from industrial fault detection all the way to the spam filter in your email inbox. It's everywhere. Okay, so now let's start putting all these pieces together. How do we take these individual tools and use them to create a kind of mathematical blueprint for our very messy, unpredictable world? So to build that blueprint, we need a special kind of ingredient. It's called a random variable, which honestly is just a fancy way of saying a number we don't know yet. That's it. How many customers will walk in tomorrow? What's the stock price going to be next week? We use these things called random variables to act as placeholders for all those unknowns. Now, here's a really important insight. Not all randomness looks the same. It actually comes in different shapes, and we call these shapes distributions. And as you can see, we have a specific tool for each kind of problem. You've got binomial for simple yes or no outcomes, like is this part defective or not? Then there's Poisson, which is perfect for modeling how many events happen over time, like customer calls hitting a help desk. Of course, there's the famous bell curve, the normal distribution, which describes all sorts of natural variations. And exponential? Wow, that one's fascinating. It models the time between random events, which is why it's absolutely crucial for predicting when the next machine failure might happen. Each one is like a specialized lens for looking at a very specific kind of uncertainty.
So, why bother with all this math, right? What is the ultimate payoff for doing all this work? Well, if I had to sum it up in one word, it would be control.
Really? It's all about getting a handle on variability. I mean, whether you're in manufacturing, finance, logistics, it doesn't matter. Instability is the enemy. What everyone is chasing is stability, predictability, and consistency. And guess what? We have a tool for that too. It's called variance, or its close cousin, standard deviation. But a much better way to think about it is as an instability meter. In a factory, low variance means your products are super consistent, really high quality. In finance, high variance, what they call volatility, means high risk. The key is, once you can measure it, you can finally start to manage it. And this is the big payoff. This is what that whole toolkit delivers in the real world. We use it to fix machines before they break. We use it to run massive quality control programs like Six Sigma. We use it to make sure your supermarket has exactly the right amount of milk on the shelves. Not too little, not too much. It helps us manage financial risk and design computer networks that stay online. It takes uncertainty, and it turns it from a massive threat into a variable we can actually manage. So, you see, far from being some dry academic subject you learned about in school, probability is one of the most practical and powerful lenses we have for understanding the world. It doesn't give us a crystal ball to see the future, no, but it gives us the tools to manage and, yeah, in many ways, even master the uncertainty that comes along with it. And all of this leaves us with a really fascinating question. As our data gets bigger and our models get even smarter, what other parts of our unpredictable world are we going to be able to understand and optimize? What future will we predict next?